Welcome, students, to day 3 of CERT-In session on Zero to Hero on assembly language, the language of cyber defender. Today, I've decided to take the input of all the students that have been calling me today. And with that output, what I'll do is that I'll try to make this class a little more basics focused for the time being. And I'll show you how I'll do that. Just give me a second. There we go. You should be able to see my screen again. It should be clearly and perfectly visible now. Beautiful. There shouldn't be any issues anymore. Yeah. So as I was saying, right, we have taken some input regarding how we should go about with the class. What are some things we should keep in mind during class? What are some areas that people are having trouble understanding, which I should maybe explore and explain a little bit more. So today, I'm going to try to address that problem. So again, today's class is called Following Your Instructions, Meeting Machine Instructions, Close and Personal. We won't be discovering too many machine instructions, new machine instructions today. But what we'll be doing is looking at the ones we already know about, like move, add, sub, a little bit closer. When I say closer, we need to understand how they affect memory again and again and again and again. And this is the thing with assembly, okay? That you might think you know everything, but you really, you realize you really don't when you start seeing the memory. You realize, okay, there are special situations, there are exceptions. There can things that can go wrong. There are things that are used the way they're not supposed to be used. Yet some programmer might use them like that. And furthermore, a lot of people have been asking me why I have not been showing a lot of coding exactly, and why my focus is towards reverse engineering. So the way I am teaching you assembly is the unconventional way. It is the way I taught myself, and a lot of other hackers that I know have taught themselves. And I believe this is the way to get into the hacking side of assembly. Because see, I do not want you to become programmers. Then you became creators, right? I want to make you destroyers and analysts. To become a destroyer, you need to not learn how to create, but get the essence of how to create so that you can destroy. So to become a hacker, you need to keep this thing in your mind that, okay, as a hacker, I will not be creating a calculator app for a mobile using ARM assembly. No, that is not what I'll be doing. I will be using that application and its system privileges, that calculator system privileges on iOS or Android, and we'll be creating a backdoor and then, finding a bug, maybe fuzzing the application and informing the right authorities about those bugs so that, you, me, and everybody else can stay safe. That is our job, right? So that is one of the reasons, I'm not going into conventional programming, like write an algorithm to do this, quick sort, this sort, that sort, DA logic in assembly. There's a lot you can do in assembly. It's just a normal programming language. You can same as well implement the entire your DAA course here. You can implement machine learning algorithms and they will be efficient. Yes, very much so. If you know your way around assembly, your machine learning stuff and your DAA is gonna be at least a few percent efficient than what you would do in something like C, and quite a lot more efficient than maybe Java. So there is of course a performance bump in assembly. There's no doubt about it, especially if you know what you're doing. That's actually one of the reasons when companies do want assembly language programmers. For example, in the game development scene, when you see any massive game being developed, you will usually see a small sector of assembly language programmers being hired, who are very highly paid because they are working on low level optimization of game textures. That happens in assembly, and some mathematics is also involved. So you must truly understand this field if you want to grasp modern computers. Okay. So once again, I'm Professor Xerox. Welcome to day 3. I'm a cyber defense researcher here at Cybervidyapeeth Foundation, and we'll be diving deep into a lot of the old topics again, because a lot of people told me that, okay, sir, I don't understand this. Maybe, sir, could you please explain this again? So I've decided to take a little bit more time, a little bit more patient approach this time around, and I'll try my best to explain it all to you in, as you know, as the pace that you want me to. So I'm not going to jump the paces this time around. Okay, perfect. So first thing to need to know is that the best way to get acquainted with the x86 machine instructions for assembly is to build yourself a sandbox to just have fun. So this is extremely important. People are go like, sir, why are you not teaching programming? See, if you want to learn how to make a calculator app in assembly, or how to make a graphics library in assembly, or how to write a driver in assembly, then make your own sandbox and go ahead, do it. It's not that hard. Instead of asking a third party to make you a tutorial on medium.com or podia.com or udemy.com, why don't just pick up the tools and start developing right and now? There are enough online resources to help you become a normal programmer in assembly. Becoming the programmer is not that hard. So if you want to get the feel of the language and you want to become a programmer for assembly, and very niche architectures in assembly, that too, there are always going to be manuals and tutorials. And if you are able to understand a single assembly language properly, usually that knowledge is transferable to other architectures such as ARM and MIPS, right? And Arduino based architecture. So microcontroller programming is also there. So microcontrollers and micro CPUs also use dial down, reduced instruction set assembly languages such as ARM. But ARM still has more compared to some micro architectures. So you will be able to implement your learnings and in these kinds of projects. And the applications are varied. For example, say that today you want to go ahead and build IoT device, and it's going to be the ultimate security solution. This security solution will contain a server, for all the logic handling. Then you'll have the master server, then you'll have the master storage where you will store all the footage from your security systems, cameras. Then you have, say, a 200 300 cameras which can cover like massive properties also, and small properties also. And these cameras are like not visible properly. And then there are like network virtualizations and network isolation happening, and then there is containerization of the applications you write in assembly, and there's just a bunch of things going on. Okay, and say you write all this is in assembly language. It's not impossible. It's been done by a few companies. It's not impossible. It's just hard to do. And people nowadays, especially in the programming space, are running away from hardware. Call me skeptical, but I believe that people in the programming space just want their job done easier now. From a time where we had to write code in Notepad, we have come in a time where IDEs such as Visual Studio autocomplete entire functions, classes, sometimes even the entire boilerplate code of your application in examples such as React Native and Flutter. So for these frameworks, usually, IDEs, you literally give them some basic keystrokes and they will write the code for you. And then there is AI-based helpers like GitHub Copilot. And these tools, they are made by humans. And just like we are flawed beings, right? We are not perfect beings. Similarly, the software and the hardware we designed is not perfect in nature. It's bound to have bugs, even the helpers. And I think, honestly, these helper programs have increased the quote unquote productivity of and the efficiency of development of applications. It has actually taken down the general security of an application if you zoom out and look at the big picture. Again, this is just my view from the research that I have done. Because you could argue otherwise, but this is just how I feel, because I've done software development for multiple frameworks across Django. I've worked on .NET. I've worked on, and commercially I'm talking. So I worked on Django, I worked on .NET, I worked on Flutter, React Native, I've also worked on Java Enterprise. So I worked on a lot of stuff that is used by most of the industry. I worked on C also, Enterprise C. So um, when you look at the tools that developers have today, you realize that things have gotten a lot easier for developers. And this is not a good thing, because when developer does not know the difference between a simple pointer to an array and a pointer to a pointer which points to an array, then it creates problem in your C code or Java code. By the way, Java also has pointers. A lot of people have this misconception that Java does not implement pointers at all. They do implement it, you just don't see it. There's a difference. So now the question comes, okay, so all this, I'm telling you, what's the point of this? The point of this is this: stop taking the easy way out. Sometimes the hard way is the right way. Take a step back, take a deep breath, and it's not going to be easy. I just said it was going to be the hard way, what the world considers at least, but it's also going to be the fun way. And I feel computers are supposed to be fun. There's this old saying that put the fun back into computing, use Linux and BSD for your own sake. And I truly agree with this statement. I feel like computers have become very monotonous. It's all about GUI development and all these new frameworks that barely add any value to your company or to your organization, when your current products are doing perfectly fine. You probably don't need them, but you always go behind the hype and the shiny thing. And that is where bugs comes, and that is where us low level hackers will fuzz those applications and will find the bugs. Now again, what is fuzzing? You will see some examples of fuzzing in day 5, don't worry. Very basic introduction to fuzzing. We won't be going too deep into fuzzing in this course, because this course is not about exploitation per se, but I just wanted to put it out there for all of you, so that you have a general idea of which side of teaching I am going for, which style of knowledge imparting I am going for. So now let's talk a little bit about how assembly language programs are different from standard programs. So for example, if you had a program that was say made for C programming language, how do you think the hacker slash novice developer, how would you go about differentiating the two programs? And those two programs do exactly the same thing. And this can be as simple as a hello world program. So say that you have a simple hello world program, and that hello world program is in assembly and in C and in Java and in Python and in COBOL and in Rust and in Golang, and in all these languages you have made the program, and you've linked it up and everything, and you just type the name of the program with the language name and it runs. So now here's my question: with all these languages being used, do you think all of them at the lowest level work the same way? Okay. I want this to be interactive, guys. So use the chat box. I can see a lot of you are in the live chat. Please use the chat box. Here's your question: do you think if you write the same hello world program for all the different language platforms and frameworks, right, at the absolute lowest level, do you think they work the same way? Okay, so I can see a lot of people writing no sir. So if you mean to say no, why no? I want a why. Okay, when your brain says no on something, then there needs to be a reason as to why it said no. And if it says yes, then there needs to be a reason as to why it said yes. So see, every language at the lowest level implements it more or less in the same way. Why is that? Is because at the lowest level, the operating system, the OS, okay, if you talk about it, the OS has something called system APIs or syscalls. 99.99% of No. Okay, so Shivam Mittal asks that all the languages would be using different kinds of syntax and instructions to perform the same task. You are correct. Their syntax is different, but isn't that syntax created by us? The work they are doing is the same. So the instruction given to the CPU to do the work should also be the same, because the CPU has a limited number of instructions it can execute, right? CPU only understands this number games, move something from somewhere, add something to something, subtract something to something, you know, exchange data from one register to the other register, exchange data from memory to register, register to memory. They only understand this. They don't understand anything else. CPU is a very bare bones logic. It doesn't have any intelligence quotient. It doesn't have any IQ. We say computers are dumb. It's actually not computers are dumb. It's the thing that runs the computer that is dumb. CPUs are just plain dumb. They don't have a sixth sense. They're just arithmetic monsters. They can do arithmetic calculations very, very fast, and some bare bones calculations that even we as humans can do. Take something from point A, put it in point B. Make a copy of A, keep A in the original place, and then put it in point B. Remove it from both point A and B. Add two numbers, subtract two numbers, divide two numbers, multiply two numbers. If I am being brutally honest with you, this is all a CPU can actually do. Now, a modern CPU has some more tricks up its sleeves, but usually, especially in the 8086 era, CPUs basically had this much capability. And for a long time, they never had more capability. Yes, exactly. Sid got it. He writes, at a lower level, programs depend on the OS completely. And you're completely right. They do. At the lowest level, OS is the one that exposes functionality. So when I compile a program written in assembly for Windows, it gets compiled to something called as PE. And PE stands for portable executable. So let me quickly, take you to a small, journey about PEs, what PEs are, before I go deeper into this concept. So I'm going to take you through a small example of what a PE is. And I'm also going to take you through what a ELF is, or an ELF file is. Okay. So these things are extremely important. They may feel like they are not, but this logic is only going to help you. So give me 1 second. There we go. So I'll share my screen again, and you should be able to see my browser now, anytime now. So here in my browser, you'll find out that here we have a portable executable Wikipedia page. So I'm gonna simply use the Wikipedia page right now, okay, to keep it simple. So it says, and I quote, Wikipedia right now. Again, all the credit goes to Wikipedia and the writers of this article. The portable executable PE format is a file format. Okay, so it's a file. We have seen the definition of a file yesterday. For executables, object code, DLLs, and other used in 32-bit and 64-bit versions of Windows operating systems, the PE format is a data structure. Okay, so it's not just a file, it's also a structure of how you keep that file data that encapsulates the information necessary for the Windows operating system loader. Okay, so we are now introduced with a new thing called the loader here. Keep in mind, okay, this is how you do research. It's okay if you don't understand everything. Just going on Google, opening things up and start to read and take notes can help you become a hacker in no time. So you see Windows OS loader to manage the wrapped executable code. Okay, so the executable code is wrapped somehow. So we've found so many clues and tidbits. This is fascinating, right? Furthermore, this includes dynamic library references for linking API and export import tables, resource management and data, thread local storage TLS data. On NT operating systems, the PE format is used for EXE, DLL, and sys, which is the device driver setups, and MUI and other file types. The Unified Extensible Firmware Interface, or UEFI specification, states that the PE is the standard executable format in EFE environments. Okay, so portable executables are usually what you are working with when you are playing around with Windows environments. And this basically, what runs on your computer, it's on Windows computer, it's PE. Okay. So there's a beautiful diagram somewhere down here. There we go. And I want to show you this diagram with a lot more details. So let me open up the diagram for you so that it's visible. And then I'm going to zoom out so that there we go. Now the diagram should be perfectly visible to all. So in here, we see a PE executable, which is designed to run inside a 64-bit Windows NT-based operating system. And NT basically means anything after Windows XP, okay? So Windows XP and anything after that, whatever has come, which has been basically the modern Windows era, is based on the NT kernel, okay? And the NT kernel is being in development, and there's been features added to it, etc., etc. since then. And here you can see this is how a portable executable looks. You first of all have some signature, then you have a DOS header and a DOS stub. These are from the old MS-DOS times, okay? 16-bit, 8-bit, 32-bit times. There's also a pointer to the PE header here. There's some other interesting stuff in here. For example, there is the time date stamp right here, which is important. There's also pointer to the simple table, which is now depreciated in 64-bit, but still existed in 32-bit. So if you're running a 32-bit executable, you may find it. You have other information about the binary, such as size of the code that you've written, size of the initialized data, size of uninitialized data, base of code, base address of the code, address of the entry point, base of data. You'll also find other interesting things, okay? Like, for example, major operating system version and minor operating system version. If inside a exe file for say calculator.exe, calc.exe, you analyze and you find the major operating system version and the minor operating system version, you will realize that this information actually tells Windows that, okay, from what operating system to what operating system this binary can run. This is how Windows diagnostic tool is actually able to identify if this is a Windows XP program, if this is a Windows 7 program, 8, 8.1 program, server program, or a Windows 10, 11 program. Okay. And there's basically no difference between 10, 11, to be very honest with you. 11 just has more bloatware on it, and it's just a new coat of paint. It's basically 10. There's nothing new about Windows 11, revolutionary at least. Under the hood, it's all the same. So here that information is also being stored, and you can see on the left side Windows specific fields, it says. And if you go up there, you see standard COFF fields, and then if you go up even more, you also see COFF headers. So this is the base, these are all header informations only, but these headers are very important. And then you have data directories. Data directories basically have most of the data about the binary stored, and then you have the section table, okay, which has some virtual pointer data and some addresses and all that stuff. Most of this, so from here to here, this portion is optional. Theoretically, you can have a binary which has data in all of this, but it's, I remember a research done, I think it was done in Black Hat, where they demonstrated that they had made a binary with every single header information filled up. But usually binaries will not have every single information, okay? It'll just be, say, 4 of this, 3 of this, and 4 of this, and some of the top header information, and that's about it. That will be your binary. So this is the structure of a PE binary. Now, I highly recommend everyone to go ahead on Wikipedia and have a look at this image, no matter who you are, okay? This is going to help you, because if you truly want to become a reverse engineer and exploit writer, Windows is the most used operating system in the world, okay? And because it is the most used operating system in the world, it means that, those who hack it also have to know it very deeply. And this is, the beginning of the journey to understanding PE executables. Now, again, this is an assembly language course, which strictly teaches you assemblies, basics, and general assembly, not, specific to a platform. We try not to go into a platform too much. So I'm not going too deep here. If you want to learn all these concepts into deep, feel free to check out our postgraduate diploma in cyber defense course. You can mail us at mentor@cybervidyapeeth.in for further information regarding that. Furthermore, I will show you the executable and linkable format now. So executable and linkable format, or ELF, formerly named extensible linkable linking format, is a common standard file format for executable files, object code, shared libraries, and core hubs. First published in the specification for application binary interface (ABI) of Unix operating system named System 5 Release 4 (SVR4), and later the tool interface standard. It was quickly accepted among different vendors of Unix systems. In 1999, it was chosen as the standard for binary file format for Unix and Unix-like file systems on x86 processor by the 86 Open project. So by design, the ELF format is flexible, extensible, cross-platform. Okay. For example, it supports different NDNS and address sizes, so it does not include any particular CPU or instruction set architecture. This has allowed it to be adopted by many different operating systems or many different hardware platforms. Okay. So here's an image. You can see ELFs are usually a little bit more simpler than PEs. You would be so much right. Okay. Honestly, PEs are just horrible. I think Microsoft should abandon PEs and go, use ELFs instead. If you take my personal advice, but Microsoft proprietary, they don't want to. So here we are. You know, of course, the Linux and the BSD world is awesome. So you'll definitely be getting easy to handle file types. Also, if you go into Unix like file systems for once, I want to give a special mention here to Dragonfly BSD and Linux. So if we go into Linux first, Linux is again known by all of you. I mean, Tux is our god and Linux is the thing right now. Everybody is developing for it. The number of platforms it supports are insane. I mean, these are all architectures it supports. Just look at the number of architectures single-handedly. You go to Windows, you'll see x86 and ARM, and even ARM they have not supported properly yet. So even after having this much support, the code base is pretty minimal and less bloated compared to Windows, and it's just a much more elegant solution. And Linux, Unix-like, and derivatives and Unix, all these three, such as BSD, all these four types of OSs support ELF binary. I have rarely come across a project which goes like, okay, I don't want to support ELF, because this lets you run packages and programs and let you compile from source code. So this is really considered a good thing. So with that, let me take you back to the PPT. So in here, let's talk about how we make a minimal NASM program. Again, I'm not going to show too much coding today also, because we have a lot of theory to cover before I feel that you are comfortable to write code. Because if you're writing code and you're not understanding it, then don't write code. So here we see what does a program required to be assembled by NASM. In truth, not much. NASM will in fact assemble a source file that contains no instruction mnemonics at all. Though in fairness, the instructions executable will not be run by Linux. So here you have section.data, section.text, use global start. You use start, you have put nop, okay, and then you have nop, section.bss. So you see, nop means no instruction, if you remember, or no operation. So it does literally nothing. Like technically it does something, but again, this is the smallest, technically not doing anything program you can write. It's a very small program written in, for an ASM assembler. As you can see, this is 1, 2, 3, 4, 5, 6, 7 lines. 7 lines. Smallest program you can write. Very simple again. Nothing too complex here. Sections, I've not really talked about them too much yet, so you might be getting a little confused. For now, just know that audio code goes into the text section. That should help you understand why inside the text section we are writing our code. If there's any questions, I'll wait for 2 minutes. Please ask your questions in the chat box. So no questions, I'll move on. So let's talk about instructions a little bit more. So we know that instructions can take operands or things to them. So NOP instruction, for example, means no operation, don't do anything, right? So it doesn't take any value or any values reference or any pointer to the value. But there may be instructions such as move that move something from some place to some place, or technically copy something from some place to some place. If that is the case, they take more than one, maybe one operand or parameter as it's called in something like Java or Python, right? So how does that work? We can have two parameters. We can have the source and the destination. So in x86, the source and destination work like so. Let me show you. Here, this is a perfect diagram. You can see here that we have move EAX42H. So we are moving immediate data. Immediate data is basically literal data or static data, okay? Data that's not changing. So 42 hexadecimal is now moved inside EAX. So we have the machine instruction, then we have the destination operand and the source operand. This is the way we write it in assembly, Intel assembly, okay? I repeat, this is the way we write it in Intel assembly. I hope I am clear to everyone here. You can also, have register to register transformation. So you can have value of EDI being saved in value, EBX moved into EBX. You can have CK going into BX. Again, you can see 16-bit, 32-bit, and 8-bit registers. Sorry about that. Yeah. Then you have destination is 32-bit memory at the address stored in EBP. So here the value of EDI is being stored. Value of EDI is being stored inside the address location of the value stored inside EBP. So when brackets are there, what happens? You go inside EBP, you find 7, you then find 7 inside the RAM, and wherever 7 is, you basically put the data there. You understood? This is like taking a Harry Potter book from your pocket and then going into the library, finding the shelf number, then going to the shelf and then putting the book there. Same logic. Always go back to my Harry Potter example, where you have 2 books in your pocket, 2 books in your hand, 2 books on the side table, and 2 books inside the library. So how would you would get up and go and put? So this example actually helps me also many times understand how memory, how stack, how cache, everything works. So if you want to imagine like so that, okay, you are sitting outside a library, in a bench somewhere, and there's a side table right on the left side of you, okay? On the side table, there's 2 Harry Potter books. Then there's one in your shirt pocket. It's a small mass market paperback. Then you have one in your hand, or maybe 2 in your hand. And then there's maybe 2 or 3 inside the library on the correct shelf on the second floor. So from computer perspective, the side table is your cache memory. The pocket that you have is your, registers. Okay. What you have in your hand is the thing that you are reading right now. If you have a home nearby, then that home is your tertiary storage, or sometimes also called secondary storage by a lot of people, which is basically your hard disk or your SSD. And if you go inside the library to pluck out more information, then you are looking for the correct spot, either through the memory address, or if you just want to, put the book in any place where there's enough space to fit the book, then you're looking for any first place that comes up that has 8 bytes. And if you start thinking from this example's perspective, you start realizing that, okay, yeah, it's not as complex. So as I said, immediate data is basically raw data. You just put in the number. Register data is taking data from one register to the other. Memory data is basically copying data from one part of the memory to the other. Also, please note, you will realize we are not doing memory to memory copies here. You realize that if we put a bracket here on ESI and then we put another one on EDX, You will be copying something from memory to memory, a location in the memory to a location in the memory, which is disallowed or not allowed on x86. I repeat, on x86 processors, memory to memory copy is not allowed. Okay, so other than that, all cases have been shown in this diagram. Now the size of the memory data. So what if you only want to work with a single character and not the first 4 characters or 8 characters? What if you don't want all 32 bits? Yeah, that is a fair question. Say you don't want to move 32 bits at once, right? You only want to move 4-bit at once. So the register EAX is 32-bit in size. However, you can use the least significant bit of EAX as AL. So if you go back to your register class and you look at the register diagrams I had shown before, you will realize that each register has a smaller size counterpart, right? EAX had AX, right? So you can, sorry, AL, which is A low, right? So the A register had A high, A low, then we have EAX, then we have RAX, right? So that is how we had the division. So you can actually have lower size registers as well, and you can just say AL instead of EAX, and it will give you access to the lower bits of EAX. If you say RAX, you will get access to all 64 bits. Okay, so to get access to all the storage, use always R. If you are wanting to use only 32-bit, then use 32-bit. Okay, EAX. AL is 1 byte in size. So AL is 1 byte in size. Well, what is 1 byte? If you remember, 0 to 7, right? 1 byte, 8 bits. And by using AL, you can bring back your first byte of each byte this way. Okay, so eat message. I'll come to the eat message program. We have a program for you. So now let's talk about EF flags and CPU flags in general. So first let's talk about flags just a little bit in computers, and then I'll come to what EF flags are. So if you want to understand flags, think of it like this. At the lowest level, how is the computer able to tell if we should take a left or a right? Or if there is a compare statement, how should I go front or back or left or right? There needs to be some form of logic that guides the system, correct? You cannot have it going completely, in any direction that it wants. That's not how it works. So if you want to understand how, um, flags are set, you need to first understand that sometimes when data execution happens in a CPU, computer executes sequentially until a certain flag is met, or maybe the execution flow needs to be controlled. Maybe you need to go like, okay, I was adding numbers, now I want to subtract for next 10 instructions, no matter what they are. So how would you go about doing that? You want to go like, okay, if this number is divisible by 2, then do this. Simple logic, right? How will you find out some number is divisible by 2? All the programmers will immediately go like, oh, okay, it's so simple, if it's an even number just divided by 2 or whatever, you will find out if it's an even number, if we get 0 or not. But how will the computer check for that remainder? Where is that remainder stored? So here the concept of flags comes in. Okay, so let me give you a very simple example. Processor status. So the status of your processor is actually described as a condition code or status flag. Condition codes refer to the information about the most recently executed instructions. Okay. For example, say you are decrementing a register that produces a 0 value. So the 0 value, ZF, also known as ZF flag, is set by the processor. A hardcore assembly programmer here might say, hey, a 0 condition has occurred. Each flag is a single bit in the flag register, the EF flags. If the last addition or subtraction produced a negative result, the sign flag is set, SF flag. Sign flag or SF flag is equal to the high order bit of the result of the operation. If sign flag or SF flag is set to 0, that means the number is positive. If it is set to 1, it means that the number is negative in nature. If you did not understand anything of what I've just said, please feel free to just go ahead and go back and listen to what I've said again. I've told you all the answers you're looking for. Please go back and listen to what I've just said again. You will understand it. It's not rocket science. There's also a carry flag. So whenever numbers are added or subtracted, carry flag represents the ninth bit. If the if we are dealing with 8-bit numbers, it might deal with the 17th bit if you are dealing with 16-bit numbers being added, because you need to carry the next bit. It might also deal with 33rd bit if 32-bit numbers are being added, and it also deals with 65th bit if 64-bit numbers are being added. With addition, the carry flag, also known as the CF flag, records a carry out of high order bit. Example: when a larger number is subtracted from a smaller one, the carry flag or the CF flag indicates a borrow. This internally represented return is based on the value of the carry flag. The overflow flag or the overflow condition, as you can see clearly, also known as OF, okay, is set when the result of an arithmetic operation on a signed integer quantity becomes too large to fit in the operand it originally occupied. OF is generally used as the carry flag in signed arithmetic. So overflow flag has some applications when we are dealing with very large numbers in computers. And when I say very large, I mean like humongous numbers. Numbers that cannot fit even with 64-bit representations and hexadecimal representations of 64-bit numbers. Then you will see some interesting things going on with the carry and the overflow flags. For now, don't think too much, but from a hacker's perspective, they are interesting. There is the directional flag, okay. There is the interrupt enable flag. There is the trap flag, also known as system interrupt, or routine flag, interrupt routine flag. There's also the sign flag, so which I've talked about. So these are some of the CPU flags that can be set, and based on what flag is set, the state of the processor change and it affects your execution. I hope I was able to make that a little clear. If there are doubts, then what I'll do is that in next class, I'll try to explain just a little bit more on this. Okay, maybe I'll write a program or two. I dissect the program in IDA, and I'll try to show you how register data moves. Maybe that might help. Okay, so if you want that, feel free to write in the comment, and please also like, share, and subscribe to our channel. And please click on the bell icon to be notified of all our streams and videos. There'll be hundreds of them coming soon. We'll be making regular free content, so please feel free to join us in this journey. So here's some more flags. Again, I've talked about some of them, not going into all of them because some of them are not that commonly used, and I'm not going to be dealing with them because this is not an advanced assembly class. This is an introduction to intermediate level class. So this is for your own information. Please just go through it. Okay, let's move on. So there's something called as flag-a-teak. Now it's a very individual matter. You'll have to check the reference to each instruction to see if it affects a flag. Please do not assume when you are programming in assembly, anything, look at the Intel assembly language manual, look at how that instruction behaves before you assume something. Let's talk a little bit about signed and unsigned value. In assembly language, we can work with both signed and unsigned numeric values. Signed values, of course, are values that can become negative. An unsigned value is always positive no matter what. There are instructions for 4 basic arithmetic operations in the x86 instruction set, and these instructions can operate on both signed and unsigned values. With multiplication and division, there are separate instructions for signed and unsigned calculation. The highest bit and the most significant byte of a signed value is the signed. If the signed bit is a 1 bit, the number is negative. If the signed bit is 0, the number is positive. Let's talk about 2's complement. Now, I'm not going to teach you how to take out the 2's complement, but I would like to tell you that if you're dealing with signed numbers, you basically take that number and you take out its 2's complement, and that number is its negative form. This is how a computer will show it inside its system in a negative format. Okay. So here, the best examples of implicit operands in x86 instruction are multiplication and division. So the multiplication instruction does what you would expect. It multiplies 2 values and returns a product. Here's an example. The divide instruction divides one value by another and gives you a quotient and a remainder. In division, you don't have a problem that multiplication has of generating large output values for some input values. If you divide a 16-bit value by another 16-bit value, you will never get a quotient that will not fit in a 16-bit register. The division instruction does not affect any of the flags. However, division does have a special problem. Using a value of 0 in either the dividend or divisor is undefined and will generate a Linux arithmetic exception that will terminate your program. Please note this is a Linux arithmetic expression, it has said. How it is generated in Windows, or if you write your own operating system, how you choose to handle it is actually up to you. You can actually code this out. If you're making your own mini kernel and mini OS, you can actually choose to see how this is handled. Here are some operand symbols. This can be considered like a small guide to operand symbols. So just have a look. I'll give you guys about a minute or 2 minutes. So let's move ahead. The signed bit is the high bit in a signed byte, word or double word. But what happens when you have to move a signed value into a larger register or a memory location? So let's try it. We move -42 to AX. Then we run the move SAX on AX into EBX. So move SX is different from move in that its operands may be of different sizes. Move SAX has 3 possible variations. You can have source operand of 8 and destination 16, 8, 32, 16, 32. 8-bit sign to 16-bit sign, 8-bit sign to 32-bit sign, and 16-bit sign to 32-bit sign. These are the only three options you can have for MOVSX. Now, let's talk a little bit about the process of creating assembly language programs again, because a lot of people had some issues with this yesterday. So again, this is all theory. I'm not gonna go too deep into this. We've covered all this before, so I'm not gonna waste too much time here. Please just read through this. If you've missed yesterday's class, consider this a refresher. Sorry, if you've attended yesterday's class, consider this a refresher. If you've missed yesterday's class, consider this where you need to pause and learn right now. Again, we are not going to be using Plex hex editor. I'll show you another hex editor that I have on Windows, but yeah, this is one you can look out for on Ubuntu. All this I've already covered yesterday, so this is all just text refresher, please. Okay. This is for the blessed hex editor on any Linux platform. Windows, I'll show you in just a second. Bless is really hard to find for Windows now, as I said, so don't worry, this is all old material. You've talked about endianness as well yesterday. Please watch yesterday's class if you want to see the explanation of the slides that are currently going in front of you. Again, if you want to explain and understand endianness, little endian is just writing the number in reverse, and then big endian is writing it how it should be. Simple to understand. So this is an interesting concept which says that text in code out. What does text in code out means? That usually when you're writing code for assembly or any language whatsoever, even machine code, if you are a god level programmer who can write binary and binary patterns, even you will be writing text files and then converting them into machine code. Okay, you directly usually you don't write machine code. Okay, some form of encapsulation or abstraction is there always. Again, we have seen this before, before yesterday we have gone through this, how the assembler assembles the program and not compiles. We've also seen what comments are yesterday. So here's the write only source code. This is a good time to point out any serious problem with the assembly language. The instructions themselves are almost vanishingly terse, and will do anything useful takes a lot of them. In addition, each instruction states where it does. There's nothing to indicate context within which the instruction operates. Without context, assembly language starts to turn into what we call write only code. The assembler and linker. When you first learn assembly language, it's unlikely that you'll be writing programs spread across several source code files. They may make the linker seem extraneous, and there's only one piece to a program and nothing to link together. So this is true. When I started, I remember I created a small calculator app. Initially, it was just one file, all logic, keeping it simple kind of thing. But as time passed, I realized that if I wanted to add a lot of features, maybe a graphics library, more functionality, security features, hide the data, some cryptography, it becomes impossible to just use single file. You'll have to have like multiple source files. Something along the lines of this is required later down the line. Again, some basic theory, just you can just read through this. You can pause and just read through this. So the linker's job is complex, and that is true. Linkers are very complex pieces of programs and are not easily described. Each object may in the module may include the following: the program code, including name procedures, references to name procedures lying outside the module. So we have seen all this. It can also have debugging information, other less common odds and ends that may help the linker create the executable file. And this other less is actually interesting. Keep this in mind that linkers can handle other types of stuff also to create an executable file. This will be useful when we get into the reverse engineering side of things. Again, relocatability, I've already talked about this yesterday, so I'm not going to waste too much time about this. You can just read through this. This is all theoretical part of learning assembly, which needs to be taught. That's why this slide is again here. If I'm introducing it twice, please make sure that you read the slide at least twice as well. Here are some linker errors. You just have a look at them. Again, most of this you have to learn and code and practice. Okay? This is all, some of this is theoretical, some of this is practical. You have to really try it out. Here's how to test your .exe file. So you need to understand something that errors and bugs are not the same. So a bug is when the code that you've written, the program that you've made, the set of instructions that you've written doesn't work the way you intended it to. Okay. But errors are basically when your program is just not straight up working. This is another interesting point. Bugs are usually not detected by the assembler, whereas errors will probably be detected by the assembler and the linker. Again, we've already talked about debuggers and debugging in general. This is not rocket science. Again, you know what a debugger does. We will use ptrace. That's all I'm going to tell you on the Linux side of things. So we'll be getting into some debuggers, but yeah, not right now. So this slide I really like. It talks about my idea of how I am learning assembly. So this is about installing different kinds of softwares on Linux. Let's not waste too much time. This is for something that runs GNOME. The Synaptic Package Manager is a pretty popular package manager back in the day. Now it's not that popular, but you can still use it. It's still in active development. You will still find it in most distributions of Linux and BSD. Again, we have seen all this yesterday. We've seen all of this. This is general steps of how to debug something. int80h is now being introduced as a syscall or a system call. Thank you so much. So as you can see, we didn't go through a lot today. So what I'm going to do is, let me stop sharing my screen. Give me 1 second before we end today's class. There are a few more things I want to show you all. 1 second. Yes. So I'm about to share my screen. I want everyone to notice. So give me 1 second. It should be visible right about now. So here what I'm going to do is, let me make it go full screen. Let me zoom in just a little bit. Let me go back to the old directory. You might remember this directory. And I'm going to show you some basic things, especially with Redare. So I'm connected to the internet, so I can just do sudo apt install Redare 2. And Redare is already installed, so we can do R2. And I want the assembly binary. So hello assembly bin. And it says Clemens included. Perfect. I'm going to type AAA 4 times here. This will analyze the binary in the Redare reverse engineering framework. There we go. It analyzed everything. Then I'm going to do a simple PDF to look at the basic structure of the file. Let me also do, well, function list. Okay, perfect. So if we do PDF, we can actually see the entry point to the executable. Okay, then we can see a bunch of move ABS or absolute value code, and we see a bunch of bytes here. Do you see this? Hello world, and then a bunch of bytes here. Padding of bytes you see after hello world. Then we see the length of the message being passed. Then you see a system call right here. Then we see a value being passed into the EX register, a XOR happening, or a exclusive OR, and then again another system call, which is usually the AND system call. So this is the reverse engineering framework, and this is the older binary. So let me see if I have another binary, and yes, I do. I also have hello bin, which has been made in a slightly different manner. So let me do hello bin AAA PDF. Yeah. So you can notice that even though I compiled it with different flags, inside it looks still the same. And this is how it looks when you are using a binary written in assembly language. Okay. So now I'm going to show you how it looks like with C. So let me do hello underscore C, not a capital C, but a small c. And it tells me that warning, you should run it with -e bin dot cache equals true. So I'm going to do exactly that. Okay. Wait, what? Did I miss anything? Or is that just a funny output that R2 has given me? Let me see again. Yeah. So that was definitely something funny. Now I can do PDF. And there we go. So this is when you had made the same executable in C language. Okay, same executable, but in C language. I'll also try to do SF main and then PDF. So now it should go inside main and show you the main code. Yes, it's showing us the main code. So because it's written in the C language and we were at the entry point where I could not see the main function, I said that set the function that I want to decompile to the main function. And then I said print the decompiled function. So it showed me the main function. Now in here, in the main function, again, there is some standard stuff. We had seen all this on Windows as well for the main function in IDA, if you remember. This is Linux, of course. And in here, you will see a push RBP, a pop RBP. You will also see things like, move RSP to RBP. You'll see the LEA instruction, which is very interesting instruction, very similar to move actually. And you will also see the call to system IMP put S. Now, if you don't understand what put S is, one of the things you can do is just quit the application and type man put S. So just try to figure out, okay, what put S is. And it says that, in the third page of the manual or the third section, which is the Linux programmers manual, we see F put C, F put S, put C, put char, and put S. And the output of characters and string they handle. Okay. And F put C writes a character to C, cast as an unsigned char to the stream, output stream. F put S writes a string S to the stream without it terminating null byte. Okay, that's dangerous actually. That can cause overflows. F put S doesn't sound very funny, fun to use. There can be buffer overflows there. Put C is equivalent to F put C, except it may be implemented as a macro which evaluates a stream more than once. Okay, that's more interesting. That's actually, I can see that being used in OS development. You have put char, which is equivalent to put C, C standard output. There's put S, which writes the string S and a trailing new line to the standard output, which we had used. Okay. So these are all system calls, and you can see, that they're all explained here. And it also tells us something called bugs. If you see right here, as security people, we should keep our eyes open when we're reading manuals. See bugs. It is not advisable to mix calls to output functions from the stdio library or standard input output library with low level calls to write for file descriptors associated with the same output stream. The results will be undefined and very probably not what you want. Okay, here's another one. I have now opened up the printf and the fprintf Linux programmers manual page. And I'm not going to waste my time reading this massive manual to you. This one's going to be a much larger one, because this this function is a lot more complex one. So even the underlying system call is a lot more complex one. So I'm just going to go down to show you the thing here. Yes. Because sprintf and vsprintf assume an arbitrarily long string, callers must be careful not to overflow the actual space. This is often impossible to assure. Note that the length of strings produced is locale independent and difficult to predict. Code such as printf often indicates a bug, since foo may contain a percentage character. If foo comes from untrusted user input, it may contain percentage n, causing printf to call to write to memory and creating a security hole. So here's a very interesting sentence that you will find inside the Linux manual itself, saying that, hey, you should not use printf. And let me ask you, how many of you, especially if you're in college or you've cleared college, have learned C and started with printf hello world? Even today, companies are, when they develop software with modern C, they're using printf. My question to you is this: why use printf? The manual clearly states that you should not. But we rarely listen to the manual. And here's another one for those who go like, no, I don't believe you. How can it be unsafe? It's not a bug, it's a feature. For those people, let me also take you through the other part of the manual. So this is for the scanf function, which is another extremely common C function being used. And somewhere down here, you should see right here. Okay. All functions are fully C89 confront, but provide additional specifications, Q&A as well additional behavior of L and L specifications. The later may be considered a bug, as it changes the behavior specifiers defined in C89. Some combinations of type modifiers and conversion specifiers in ANSIC do not make sense. While they may have well-defined behavior on Linux, this need not be the case on other architectures. It's usually better to use modifiers that are not defined by ANSIC at all. So if you've learned ANSIC, and I would like to point this out, if your college has taught you ANSIC, it's not the C that's usually deployed nowadays, okay? And you should not be making your programs with ANSIC, okay? So let's end the class here today. I've shown you another tool called Redare. I've taken you through, the features or some features of Redare, some shortcuts of Redare. Here's a manual of Redare. You can also again install it yourself on your Ubuntu or Debian based system and actually go through the different features of Redare. The documentation is fantastic on Linux. There's no doubt about it whatsoever. And I would like to, once again remind you about our course, which is post-graduation diploma in cyber defense. It's a 1-year long intensive course that tries to explore all the limits and boundaries of cyber defense engineering. The admission is still open as of right now. It is still open, and you can use the information on your screen right now to further query us regarding the course. Feel free to contact us on mentor@cybervidyapeeth.in. You can also visit our website at www.cybervidyapeeth.in or call us on 971 1147 You may scan the QR codes available on your screen right now to join us on Telegram, apply now to the course, or to connect with us through our connectors forum. The course is backed by Vinobha University, Government of Jharkhand, and the University Grants Commission of India, and it's taught by us here at Cybervidyapeeth Foundation. As I have mentioned before, the course will contain all these topics that I'm teaching, but in an extremely advanced manner. We'll be taking you from zero to absolute elite level hacker. You will be going and learning each and every concept in detail. We will not be leaving you, with just manuals. We'll be explaining each and every line of the manual. You will be playing around with BSD kernel, Linux kernel. You'll be building your own mini kernels. And there's just so much to do. So we hope to see you there with us. Thank you so much for joining me here for day 3 of Zero to Hero on CERT-In session on Zero to Hero assembly language, the language of Cyber Defender. I hope to see you there for day 4 of our session. If you have any questions, feel free to ask them in the live chat or the comment box based on when you are seeing this video. Thank you so much for joining me. Dhanyavad. Jai Hind.